Good morning. So this is our 419 Computable General Equilibrium Models, and this is our last lecture. Since this is the final lecture, I want to first give a brief overview of what we have done in this semester. And then I want to introduce you the dynamic general equilibrium models, dynamic stochastic general equilibrium models. This will be a very brief, very short overview of these dynamic models, but I want to show you how we have studied these things. So in the literature, especially in macro now, if you want to study macroeconomics, you have to deal with such dynamic stochastic general equilibrium models. Okay. So let me share my screen. Okay. So let's put this over here. So for the overview, remember that we first studied the positive properties of general equilibrium. All right. So what were these? Well, we have the existence problem. We have the uniqueness problem. And we have the stability problem. All right. Then we studied the normative properties of equilibrium. And typically, what we look at here is, of course, the first fundamental theorem of welfare economics and the second fundamental theorem of welfare economics. Okay, so basically, remember the first theorem tells us that competitive equilibrium, or the general equilibrium, is Pareto efficient or Pareto optimal. And the second theorem tells us that any Pareto efficient equilibrium could be implemented as competitive equilibrium if you have the ability of redistributing endowments initially, right? So first we want to change the initial endowments, then we let the market behave again under competitive conditions. So that type of competition then allows the market to go to the desired equilibrium. Okay, so after that we also discussed envy-free and fair allocations. Okay, so those were also important concepts for us. Then we studied a toy model. Remember, one household, one firm, one production factor, and one good, right? So that was a toy model that we used to understand the logic of the general equilibrium. All right. Then we looked at the model in chapter 3. Okay. Now in that model, there was no government, but there were firms. So there were households, so there could be many households, right? There could be many firms, and there could be many production factors. So we studied that economy. Then in chapter 4, we introduced government. We introduced saving, etc. So we extended the model. Then we started studying social accounting matrices and calibration. Okay. So there is, as you remember, SAM data, and there is SAM model. Okay, and SAM model depends on model's parameters. obviously, right? So calibration is basically using SAM data and the model, of course, to recover theta values. Okay, so in most cases, it's a very simple exercise, right? Then we had some examples, of course. Last week, for instance, we see a model where there are two firms, one using dirty technology, another using green technology. And then we use taxes and subsidies and how they affect equilibrium allocations. We basically studied that. So this is the general overview. This is what we have done in this semester, and I think that gives you the general idea of how general equilibrium models work. Okay, of course, if you want to do this as a researcher, you must be really careful in many different dimensions. It is generally not very easy as in the textbook, but still, this is the fundamental approach to general equilibrium modeling, and how do you really apply such models in your research. So of course there are other dimensions. Okay, other dimensions. One is, as I said, and today I'm going to cover this a little bit, dynamic stochastic general equilibrium models. Dynamic and stochastic. Okay, I will give you a brief overview again. Then there are also there's also this network approach. Now, in the standard model, we of course have the input-output matrix, right? So this is what connects different sectors in the economy, right? That matrix basically connects. So that matrix represents the interconnections within the economy. But there are other approaches. So you can more generally define. You can introduce other types of connections here, not just input-output coefficients. All right. You can talk about, for instance, location. You can talk about technological spillovers. So what's the spillover? Well, suppose that there's this firm using a particular technology and other firms located near to that particular firm benefit from that type of knowledge as well. All right. So there is then other types of models where, from a mathematical point of view, you see the the network effects in different dimensions, not just depending only on the input-output relationships, but other types of relationships. Again, geography is important. So in general, location is important. Technological spillovers play a big role in such a setup, etc. Okay. So I'm not going to, so we usually have no time to study such a network approach because it requires a little bit of advanced math. But I will give you, again, today, in the rest of this lecture, I will give you an overview of the DSGE approach. Okay. So let's try to understand that. So first of all, let's look at the household side. All right. So we had this utility function, remember. So I have CIH, right? So C2H ... CNH. Okay. Now, of course, this model has no time, right? Now we want to introduce time into this framework. How do you do that? Well, time can enter as a discrete variable, right? Or In that case, this is called discrete. Or time can enter as a continuous variable. Continuous. Okay. So we want to understand that how can household choose consumption across time? Well, then we must have something like this, right? So remember that income was about the endowments, right? So P1, E1H, P2, E2H, right? These were the endowments. So there are production, sorry, so this is not P, omega 1, E1H, omega 2, E2H, dot, 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 omega K, E, K, H. Okay, so this was income. Now, when we introduce time, of course, we have this. Let me use a different color. So we have time. Now things are changing in time, first of all. Okay? Things are changing in time. We allow this possibility. Then now this income now will be greater than or equal to consumption, right? P N C N H. And once again, these are changing in time. Now realize one thing, if there is no saving, right? If there is no saving, once again, you find the demand functions, right? And these will be the same demand functions. Once again, they will depend on price vectors, all right? But now, this is changing in time because prices are changing and factor prices are also changing, okay? But once we introduce savings to the model, then it will be a little bit different. Why? Because now we have to be careful about the future consumption. So in that particular version, consumer only cared for the current consumption, right? Consumption at T. So basically there were goods and this consumer cared about the current consumption, okay? But then we may also have this. Consumer caring about consumption in the future, okay? One period further, okay? It could be 2 periods further, etc. Then how can we do that? Well, you can write the problem more generally in this way. So there is this utility function, okay? And this is your consumption vector. Now it is a vector that changes in time, okay? And then you want to maximize this. I will explain what this is. You want to maximize this in this way. So there is your income, okay? Let's say your income is originating from asset ownership, okay? Let's say you have an asset stock, and also let's say you work and obtain labor income. Now that income is to be spent on consumption, at each t, right? So you have P1t, C1t plus dot dot dot, PNT, CNT. This is what happens at t, plus you have the saving. Okay? Now realize that this is now a dynamic equation, right? Because this will be in the next period, this will be your asset stock. And why is that important? So here beta is called the discount factor. Discount factor. Why is that? Why is that important? Because today is more important for us. Here, consumer is impatient. Okay. Future utilities. So this is, if this is your big utility function, future utility flows receive a smaller weight, right? Because if beta is between 0 and 1, beta to the t goes to 0. Okay, in the future, so today is more important for me. Okay, I attach greater importance to present. Okay. Obviously, this problem is a bit harder to solve. All right, because I want to choose once again consumption levels, but also I want to leave a particular amount of assets to the future. Why is that important? Because today's asset stock and my consumption decisions today will affect my asset stock tomorrow. Then my consumption decisions tomorrow will affect my asset stock in 2 periods ahead. Okay, so this is the chain reaction, and that goes on. Then I will choose my consumption again, and that will affect my future asset stock. Okay, so I want to do this in such a way that this sequence of consumptions, right? I mean, there is now a sequence of consumption levels. So these are maximizing my utility. Okay. So there is, of course, a particular way of doing that. You can use Lagrange, you can use other more advanced methods, but it can be done, and eventually you can understand how you should decide, how you should choose your consumption and savings. Okay, under certain simplifying assumptions about utility functions, about the formation of these prices. You can actually characterize the solution. One thing important, of course, one thing that is important is that you take the prices as given. Okay, and you take these as given for all t. Okay, that is, of course, a strong assumption, but this is usually what we want to do to solve the problem. Now, for a firm, now imagine this. Imagine this very simple characterization of the value of a firm. Okay. So here we write the value of the firm in this way. So R here is some interest rate. Okay. So typically this then becomes the discount factor 1/1. So here beta is 1/1 plus R. Okay, this is the correct way to discount the future if market interest rate in real terms is R, and pi t here is profit. Okay, so what's going on here? If you want to calculate the value of your firm, and if you want to maximize this, you want to take your decisions, you want to choose your choice variables in such a way that this whole thing is maximized, not just the current profit. Okay, now current profits, of course, will be again written, you know, there will be a price. Let's say this is the, this is firm I, okay? This is firm I. So there will be a price and there will be production. Let's say production depends on capital stock and the labor that is employed by the firm. Then there will be, of course, the payment for labor. Let's say this is payment for labor. And then firm will make an investment expenditure. Okay. So then what does this firm actually do? So there is, of course, now this dynamic equation. As in the consumer's case, there is also a dynamic equation here. So suppose that the firm's capital stock changes in this particular way. Okay. Now, what do we have here? Delta is between 0 and 1, and of course, this is depreciation rate. Okay, delta is the rate of depreciation. So the net addition to your capital stock is gross investment minus depreciation. Okay. Now, what does this firm do? This firm will maximize by choosing labor demand and investment level, okay, by taking into these constraints into account. Okay, and once again, the firm will be a price taker. The prices, oh, by the way, these prices do not depend on okay, so these prices then will be given to the firm. Okay, so once again, you can use a Lagrange, or you can use other methods such as dynamic programming. So these are a bit, this is a bit advanced, but that's how it works. Okay, so this is how you actually create a dynamic version of your general equilibrium model, because we know consumers will be caring about future, firms will be caring about future, and their decisions today will affect their constraints tomorrow, right? How? Well, as you see, my decision today, my investment decision today affects my production level tomorrow. Okay, look at this. In the case of consumer, let me show you again. In the case of consumer, my consumption today affects my asset stock tomorrow, and that asset stock, of course, in the second period, you will have this, right? AT plus 1 plus WT plus 1, AT plus 2. So with such dynamic trade-offs, you should be careful. Now, dynamic part is done, roughly. Now let's talk about the stochastic part. Okay. First, think about the production function that I just have written. there's capital, there's labor, right? So this production function, let's say, is Codd-Douglas. All right, so you have alpha and LTI 1 minus alpha. Okay, now as you see, this production function is deterministic, right? So if you have let's draw it. So if you have K here, L here, then you always get FKL, right? So the particular input combination gives you a particular production level. Okay, so it's around let's say here. Okay, another combination will give you another level. Okay. You can now introduce technology shocks. Suppose that there is this term, let's say e to the epsilon t, okay? Now, this is your production. Now, this term, suppose that it is distributed with zero mean and constant variance, and it is distributed normally. So what's going on? Well, now, even if you fix your capital stock and labor demand, your production is changing stochastically, right? It is distributed depending on epsilon. Okay, because epsilon is now your technology shock. If epsilon is positive, you become more productive, right? For positive levels of epsilon, there's more production. For negative levels of epsilon, there's less production. You become less productive. Okay? You can also imagine the consumer problem, and you can introduce preference shocks. Now, suppose that consumer cares about income, but there is this shock to the preferences. Okay? What type of shock is this? Well, it can affect your risk aversion. Okay? It can affect other dimensions of your choice. You can also imagine this. You can also imagine that your discount factor is a function like this. And the shock affects your discount factor. Now you see the discount factor would be something like this. So F T epsilon, for instance, could be beta to the T plus epsilon T. Then you have something like this. If this is your discount factor, if this is time, you have this, but there is now the confidence band around your discount factor, right? If epsilon is positive, you are there. If epsilon is negative, you are there. So there is now your discount factor. If you look at it, it can change in time. Okay, then this becomes a preference shock. Now, as you see, I can extend my model with shocks under the assumption that I know the probability distributions. right? So in general, we have three types of shocks: preference shocks, technology shocks, and policy shocks. In a model, in a macro model with many different countries and different countries borrowing from different global actors in the financial markets, then you can, for instance, have risk premium shocks. You can have other types of structural shocks that affects your economy, All right, there could be many. Now, the general way of understanding such models is once again to develop a system of equations. Okay, only this time this system will be a little bit different. It will be like this. So there will be an expectation, and there will be a function of dynamic equations. I'm just going to explain what all this. Okay. Now here, what you see is this. So your YTs are called control variables. There are many here. Your XTs are called state variables. So in our examples, we have KT for the firm, AT for the household, etc. Okay, and these are consumptions, prices, and other stuff. Okay, L, for instance. Okay, other stuff. Then you have the shocks. And again, now, what is the dimension of your system? Well, let's say you have n endogenous variables, n control variables, and m state variables, okay? Then this function here, there are n plus m equations. Okay? And this one is, of course, expectation. And F here is typically nonlinear. Now, how many endogenous variables you have? You have n plus m endogenous variables, okay? And then you have these equations. Here, of course, we still be careful about Walras law, okay? Walras law is satisfied in such models, okay? Then at the end, your solution is like this. Your solution is like a numerical solution, but it is like this. So there is a transition equation, okay? And there is a observation equation, okay? Because decision makers base their decisions on the current state, and the state is evolving, all right? For instance, here you have capital accumulation, asset accumulation, right? So these are depending on other stuff in the model, and they depend on shocks. And then you have your you have your control variables. By looking at the current state, you find your decisions. So this is called the state space form. And there's a particular, there's a set of particular methods that we use. Usually, we again use computers to do all this. Okay? So that's all I want to discuss about dynamic stochastic general equilibrium models. They are pretty commonly used. There are many critiques, and some of these critiques are pretty important. So DSGE models do not solve all our problems. Okay, so they are not just the end of the story. There could be many different mechanisms that are involved. Usually we make a lot of simplifying assumptions, and usually the meanings of the shocks are not sometimes very clear, and so some people are criticizing the use of DSG models, and some of these critiques are especially important. But at this level of your education, I think it's enough of DSG models. I mean, it's good to go. So you have now an understanding of how you can write dynamic and stochastic general equilibrium models. Okay, questions, comments? We can reconnect again to discuss if you have questions or if you want to discuss certain things. Otherwise, I'm gonna call it a semester. You have less than a minute. Yes.
Hocam sizin geçen haftalarda verdiğiniz bir calibration sorusu vardı ya.
Evet.
Onu sizinle çözme imkanımız var mı acaba? Ben biraz yaptım ama çok başarılı olamadım devamında.
Tamam. Onun zaten çıkmıyor olması lazım. Sen bana mail at, ben de sana çözümü mail göndereyim istersen. Ya da şimdi connected olup bağlanalım. Ama onun çözülmüyor olması gerekir.
Ha, okey o zaman. Olur hocam, ben size mail atıp siz bana atarsınız.
Sen bana bu bulduklarını gönder. Ben kontrol edeyim. Sana modelin parametrelerini gönderirim.
Tamam hocam.
Aslında kodları yükledim. GAMS kodlarını yükledim bu arada. Oradan da bakabilirsin.
Hocam. Tamam.
Okey. O zaman final sınavında görüşürüz.
Teşekkürler hocam her şey için.
Kendinize iyi bakın. Ben teşekkür ederim.
Hocam.